Hello, everyone, and welcome to this Dynaflow Discussion session. I'm here with my colleague, Mick Bouman. Mick Bouman is a project engineer at Dynaflow. My name is Johan Bosselaar. I'm a senior engineer here at Dynaflow. And today we're talking about safety factors in piping industry. Mick, welcome to this session.
Yeah, thank you very much for the
Yeah,
introduction.
nice that
Uh,
you're here. And can you tell me a bit more about yourself?
yes, so I've been a project engineer at Dynaflow for about 12 years now, starting from 2010. I've worked on a lot of different, say, projects that Dynaflow does, and among one of those projects is, or those type of project is the design of FRP piping systems. And due to my and also our experience as a company, I was asked to join an ISO working group on the
Okay.
design of a specific type of FRP or fiber reinforced plastic piping. And there has been quite some development in that standard, in which I was involved as well. And there was a topic on safety factors that I think was very interesting, and that quite some people may not have heard from. So
Okay.
I
So,
thought it was interesting to
and if
have
I
you.
look at the screen, I see that that's a member of the ISO TC 138. What does that mean?
Yeah, so the ISO standardization as a body has all
Mhm.
kind of task as a committees or task task committees that deal with specific subjects. So some part may be of steel structured design, some part may be of buildings and bridges or whatever. And this TC 138 slash SC6 uh, tells you something about the typical subjects that all the standards that are developed in that group or in that say subcommittee, what the type of subject is. And in this case, it is always uh, it has something to do with the design or the testing of glass reinforced piping, so pressure piping in this case also.
Okay.
And the
Okay.
specific working group, so under that subcommittee, working groups are defined, and they have, say, experts in them that have something to say or have had experience with a specific topic, and they
Mhm.
are asked to uh, make standardization documents. And
Okay.
one of
And
those standardization documents is the system design of above ground pipe and joint installations without entrust.
okay, nice. And
Yeah,
how many people are in this working group?
this working group, it depends a little bit because in principle, every country is allowed to have a certain amount of people in the group. So there is a small core group with some people who are working at flow tight pipes,
Mhm.
at future pipe, at NOV. Um, they're all manufacturers of piping. Then we are there as the engineering consultant with our own expertise. And there are a couple of people who are more involved with the drafting of the document itself. So the write up and making sure that it is a proper ISO document.
Yeah. Okay. So it's different types of uh, experts are really in the
Yeah,
in the in
yeah.
the working group. Yeah.
So
Yeah.
some are more practical and some are a bit more, say, analytical, like us.
Okay. Nice.
Yeah.
Okay, yeah. So before we move on, I would like to invite everyone that is watching to write down their questions when they have them inside the live chat. Yeah, we will be monitoring the live chat. So if anyone has an interesting question or yeah, uh, please ask. Then we can discuss that during this live session as well.
Or
And
perhaps at the end, if it's a bit unrelated to the
Yeah, if
specific
it's
topic. Yeah.
unrelated, we'll put them in the end. If it's really related to the current discussion, then yeah, we can immediately talk about it. And yeah, so let's move on.
Yeah. So first, I'd like to give a short overview of what kind of pipes are meant or dealt with in that standard. So what you see at the right are a couple of examples of above ground piping without entrust. And in a normal pipe that is welded, or perhaps it's jointed or flanged, there's always pressure thrust inside the pipe, because there's
Yeah.
always an end, that could be an elbow or an end cap, where the pressure acts, and that creates a tensile force in the pipe wall. For these kind of pipes, that is not the case, because the end thrust that is being taken up by concrete blocks or some kind of supporting structure, and the pipes themselves, they are not joined by a material that can transfer the load. So in this case, these are coupler joints, and they provide a seal against leakage, but they can't say transfer so axial stresses
Okay, so
from one
they're
pipe
like
section to another.
loosely connected to each other or something. Can
They
they?
are loosely connected. Yeah, they if you apply enough force, you might be able to rotate them. However, there's also quite a lot of friction inside these joints, so
Okay.
that is actually quite difficult.
Yeah.
And yeah, the interesting thing of having a piping system like this is you can treat each part as a separate part. It's more like Lego blocks,
Mhm.
and yeah, they are mainly used for the transport of, you say, potable water, or for hydraulic energy plants. And
Okay.
yeah, they come with their specific challenges.
Yeah. So and
Yeah,
is it like a high pressure or low pressure application?
typical, the pressures are not that high for these systems. So
Okay.
there will be 4, 6, perhaps 10 bar. You could make them higher a little bit still, but it's
Yeah.
not 100 bar pressure piping. So it's typically large bore, because it's a transport of a lot of water.
Hmm.
Yeah.
And so is it relevant to use steel, for instance, for these kind of piping, or is it mainly just the fiberglass that you just talked about,
Yeah.
fiberglass piping?
You could use steel, but that has its specific problems related to corrosion. Yeah, so in this case, the uses of FRP materials, yeah, is quite a bit cheaper normally,
Yeah.
because you can install them, and then you won't have to replace them for about 50 years. And for steel, that will be a bit more expensive, because you would have to use specific alloys that are capable of dealing with yeah, the medium, in this case water, which is
Okay.
actually quite corrosive.
Yeah.
So in that standard, we address the design of the supporting, and so how these things can be clamped, and some specific details on how that should be done, as to not, say, damage the pipe. Yeah, the pressure stresses in the pipe wall, so the circumferential pressure stresses, they are addressed as well. Yeah, due to friction, and due to the Poisson contraction, you introduce some axial stresses as well. But an important mechanism of failure for these pipes is the buckling, which we will treat a bit later on, because that is quite a non-intuitive subject. And so, as I said, that the various piping segments, which are quite often about 12 meters in length, they are joined by coupler sections, or coupler joints, and they cannot transfer the axial, say, load. And in that specific load configuration, existing bending moments, they are magnified by the internal pressure.
Okay. How are they magnified by the internal pressure?
Yeah, so as you can hopefully see is that when you have a pipe like this and there's water inside, then the pipe will sag somewhat. It will bend.
Yeah.
And that means that the bottom of the pipe is going to be under tension, and the top is going to be in compression.
Mm-hmm.
If the pipe is under tension, at the bottom, the amount of internal surface area is slightly larger at the bottom than at the top.
Oh, yeah.
That means that when you pressurize it, and since there's slightly more area at the bottom for the pressure to act on, there is a net force, say, laterally.
Yeah.
In a normal pipe, there's always the axial stress as well, or the axial load, and that's stabilizing. But here in this case, that load is missing. And that means that the initial bending moment stresses actually, or deformations, they are magnified by the pressure.
Okay. Oh, that's interesting.
Yes.
Yeah. So that's only for these kind of coupled pipes. It's not for your normal typical steel application with no couplers.
No, true. Typically not. It could be that if you have a steel pipe which is completely fixed in between 2 points, so that there is no pressure thrust, then you may have this failure mechanism as well. But in a normal piping system, you will not see that that often.
Oh wow! Yeah.
Well, since this standard was addressing this type of failure mechanism, and this has not been addressed that often, we had to think of, say, safety factors. How are you going to define safety factors for that? So, and for that, I'd first like to go to the definition of a safety factor and try to build our ideas from there. So, what is a safety factor? This is a common definition of the safety factor. So in selecting member sizes and materials, the designer must ensure that the failure load is safely above the design load. That means that if you do your calculations and you get a certain stress or a certain load, that has to be sufficiently below the failure load of the material. Okay. And the, say, separation between these two, the failure load and the design load, that is called the safety factor, and the ratio between. In the next slide, I show it graphically as well. So a typical failure load is the yield stress of a material, and that's is the case for steel piping, of course. It isn't the case for FRP, but since most of the people have an idea how steel works, I'm talking about steel at this moment. Yeah. So the failure stress is quite typically 240 MPa for typical carbon steels. If you divide that value by the factor of safety, then you get at the maximum allowable stress. The
so
factor,
it would be if you have like a higher stress than your maximum allowable stress, it would typically not fail, right?
Yeah, typically it wouldn't fail because your failure stress is, but what is going to happen then? Why do we need that factor of safety then? And you can ask yourself the question, what is the factor of safety based on? And it's quite a lot of safety factors that are used in the industry. They're more or less empirical. So they haven't been rationally defined, but they have been refined. So start out with a value, make a lot of products, or in this case, boiler and pressure vessels. See how many failures there are, and if there's too much, then you need a higher factor of safety.
Okay, so there have been a lot of failures in order to get to the safety factors that we currently have. Is that correct?
I don't have the graph here specifically with me, but I remember that there's a graph, and that is somewhere in an ASME, say, textbook, and that shows the amount of boiler failures failures in America. And it also shows the introduction of the boiler and pressure vessel code and the change of certain safety factors. And then you really see a sharp rise due to a lot of new boilers being developed or being made. And then you introduce a standard, and then the amount of, let's say, failures drops quite dramatically.
Oh, okay.
Yeah,
Because there are safety factors in those standards instead of
safety
just
factors in those standards,
yeah.
and the quality of the product increases. And
Yeah.
then suddenly they saw, we had to increase the safety factors because we were seeing again a lot of failures.
Yeah.
So, and these things, they have grown more, say evolutionarily than purely rationally. So but we didn't have that much experience with this type of failure mechanism and how you would address that and what kind of safety factors there are. So we needed a different kind of framework to think in.
Because in your case, how widespread are these FRP applications with these couplers? Is it used all over the world, or is it just a very specific type of application?
It is a specific type of application, but it is used. So I know in Norway it is used quite often for hydro plants.
Okay.
I can't provide you with a number here.
No, okay, but it is widely spread all over the world. But for certain,
it was widespread enough to say generate a standard for it.
Yeah.
All right. So let's go back to our problem that we had in our standard. Perhaps we explain it a little bit more initially, because here is a schematic as well. This is a schematic representation of a pipe. And if you apply a self-weight or perhaps introduce water, then there will be an initial deformation of that pipe. If you then apply a pressure load to it, you see that the initial deformation is actually growing, just like this. And we had to define, say, safety factors. But the interesting thing is that you need a safety factor for, say, a bending stress, because in this case, the effect you are describing is the bending stress, but it has to include the effect of the pressure as well. And so there were a lot of things involved, and we had to think of or we had to search for a new framework of defining safety factors for that.
Because do you have like a pressure dependent safety factor or something like that, or do you have?
It isn't a pressure dependent safety factor, but depending on the allowable pressure, the safety factor of the bending moment had to be defined, or the other way around. So there was a lot of intercommunication necessarily, and we couldn't think of a way how to do that purely based on our intuition. So we had to use a more rational framework.
Okay.
So if you go back to the classical view of how you design using safety factors, then there is a failure stress, which you can also call the stress resistance or perhaps load resistance. And that's the ultimate state that you allow or that it can have, some kind of thing. In this case, it is a pipe. And then you have a safety factor. You reduce the ultimate resistance with the safety factor, and then you have your maximum allowable stress. But how big your safety factor is, that's a very, is a loose topic. What are you going to base that one on? And there is a school of thought that is also present in the Eurocode or the Eurocode 1990. And there, instead of using with these or dealing with these fixed, ultimate values and allowable values, or say calculated values, they deal with distributions, because in reality, the resistance of the material or the capability of the material is not a fixed value. There is a distribution.
Different manufacturers, different manufacturing techniques, something like that.
Some guy sleeping during the production or during testing. We don't know what it is, but there is variation.
It's also maybe installation, or does that entail other factors?
In principle, the installation, it can be have an effect on the resistance of the material as well, and that's very important also in say FRP systems. So there is on one part the resistance of the material, and on the other part there was the effect of the actions. We can call that, for instance, the calculated stress in this case. And the calculated stress, we calculate an average value, which is more or less fixed. But in reality, my diameter can be slightly off, the load can be slightly off, the weight can be slightly off. So all kind of things, they can be slightly off. So there as well, there is a kind of distribution. And where these distributions overlap,
so that's small.
That's where failure can occur.
Okay.
Right. So let's go here.
So you don't want these graphs to overlap, right?
Well, there is always going to be an overlap.
Because
it's a normal distribution, and there's always a slight chance that the calculated stress is a lot higher than what I have designed it for.
Okay. And so is there like a percentage allowed failures, or so how do
that is more or less what it is. If your calculated effect, so your calculated stress is the mean, so to say, but there's all kind of variations around that you don't know specifically, and that can be the input parameters to your calculation. Then there's the resistance, which is an average value, and there can be all kind of variations, say, around that. When the resistance is lower than the effect of the actions, then you have a failure. In that case, the overlap of these two graphs is the likelihood of failure. And what you do by applying a safety factor is you're reducing the likelihood of failure. Because if you would say overlay these two graphs, then like you would have a 50% chance, right, of failure. And we are looking for a very small chance of failure. So the graphs, or the probability graphs, they are impacted by the variations. So variations in properties of the material, or the variations in the input for the calculation, and perhaps also the uncertainty of the calculation itself. Sometimes you have to approximate the real situation with a simplified model, but the simplified model is not 100% say accurate. And if you have low variability, that means that these the graphs, or the probabilities, they are quite small, and they're well centered around the average value. That means that you may apply a slightly lower safety factor. If you have a large variability, then the amount of overlap is also quite large. So then you would need to increase the amount of safety. And by increasing the amount of safety, you are in principle separating these two probabilities from each other. And you're separating then the average values from each other.
Would it also be possible to decrease the variability of the graphs?
Yes. So we're not going into that into a lot of detail, but in the because it's like a 50-minute talk. But in the standard, there is there's always, or there's also definitions for a certain kind of say supervision. So if you do a lot of checks and balances during the analysis process, then you can decrease the amount of safety.
Yeah.
If, for instance, you have a small project and you want to do certain things quickly, then you can use higher safety factors, which allow you to have a bit less overview and do things a bit quicker.
Okay.
Yeah. So how do you define then a safety factor in this framework? Well, first you have to define an allowable likelihood of failure. The EN 1990 specifies the allowable likelihood of failure. This value is about 1 in 10,000. However, it doesn't specify, is this 1 in 10,000 systems, 1 in 10,000 pipes, 1 in 10,000 joints, but the value is 1 in 10,000. And the whole calculating framework is built around that. And you can also define lower likelihood of failures that you need for your system, and that will increase the amount of safety, or they call it partial factors, because it isn't actually a safety factor. It's just to decrease your likelihood of failure. If you have all your variabilities, you can throw these into a kind of mathematical framework, and that will then give you the final part factors that you can that you have to apply to your pipe.
Okay.
Yeah, that was more or less my my take on this. Yeah, it was new to me, and I hope that you have learned something from it as well.
Yeah, it's very interesting. So especially how you define these safety factors. So normally you learn as an engineer, you learn the safety factor is like 1.5, 2.4, 3, you know. But you never really know what it's actually based on.
No.
It's quite interesting. Yeah.
Yeah. So it seems to be that there are more and more working groups, especially in the FRP standardization committees, that are looking towards having such a little bit more rational framework for defining safety factors.
Yeah. So how has that been done in the past then? Was it just I don't know, let's just say 2 or
there have been, so everything has probably been evolving, and so part of that is experience, and part of that is stealing from another standard. And this is the way how that has gone. Stealing a bit from other standards, and also just applying a bit of rational thought, and how certain things could impact, but not that often have people used the true probabilistic failure.
Yeah, I can imagine that just stealing it from a different standard isn't sufficient for fiberglass material, right? Because it is quite a different material than, for instance, steel.
Yeah, true. So it is also very important always to use, material properties and calculation methods and safety factors within the context of a single code. You shouldn't go shopping between standards using material properties from that and a calculation method from that, because it is a single framework that works as a whole. So you shouldn't go shopping. However, if you steal rationally, that is also a good way, because the experience of the past should weigh in on how you design new systems.
Yeah.
So it isn't that bad actually to use values that have been used in the past successfully as well.
Okay.
It's part of being a good engineer, I would say.
Yeah. Not to be too creative with your safety factors, but to keep thinking critically, right?
Yes. Yes.
Yeah. Okay. Well, I want to thank you for your presentation, and so we're at 30 minutes now, so I think it's a nice time to wrap up.
Yeah.
And
Let's call it a day.
I learned a lot. I hope everyone that is watching has learned a lot as well. So thank you everyone for watching.